free body diagram means we free a body from rest of the thing. We isolate the body from rest of the system and we look at the forces which are acting on that body. That diagram, basically we draw the force vector on a body. That diagram is called free body diagram. Now let's start with the simplest possible situation. There's a block kept on the floor. We want to draw the FBD of this block. That means we want to draw the force vectors acting on this block. Now first of all, we have to know what are the force vectors acting on this block. The force vectors, by the study we have done up till now, we can easily say there are two forces. One is gravitational force. So first thing, you have to isolate it from the rest of the thing and make only diagram of the body you intend to make free body diagram of. So one of the force acting is mg, gravitational force. This is always going to be there. And to counter this force, because it is an equilibrium, there will be a normal reaction from the surface which will be acting upward. So this diagram of the block is called free body diagram. The diagram which is showing the force vectors acting on the block with proper direction. Now the magnitude, as we have seen before, that the length of the vector, that is indicative of the magnitude of the vector. If this is what we are drawing as 10 Newton, then 5 Newton would be of half of its length. This would be 5 Newton. But in free body diagram, we don't follow it stringently. Now there is flexibility given in the length of the vector. The length of normal reaction could be shown a little shorter. It's not, we don't take it very stringently, very strictly that the length of mg and n has to be the same. It is only indicative in free body diagram. So you don't have to worry about making the vector of mg and normal reaction exactly the same. You don't have to use the ruler for this. This is only an indicative diagram. But we do know from the static equilibrium condition that this body is at rest. So from there, n should be equal to mg. So normal reaction helps to write the equation. Free body diagram helps to write the equation, and free body diagram is an indicative diagram. It includes the forces which are acting on the body with proper direction. So let's draw the free body diagram for this situation. This is m1, this mass is m2. So let's start from m2. We are going to draw the free body diagram of m2, meaning we're going to draw all the force vectors with proper direction acting on m2. One of the force is m2g, gravitational force acting downward. The other force will be from this surface, the lower surface of m2 and the upper surface of m1. That will be normal reaction. Let's call it n1. So this is the free body diagram, and there is no other force acting on m2. That's it. There are only two forces. So that completes the free body diagram of m2. Let's move on to m1. To draw the free body diagram of m1, we have to show all the forces acting on m1. One obvious force is m1g. m1g is going to act downward. Now m1g is going to pull this block downward, so surface is going to be pressed by the weight of m1. So the surface is going to offer a normal reaction to m1. So there will be some normal reaction from the surface. Let's call that n1. This was n1, let's call that as n2. Now this normal reaction is from the surface. Now there will be some normal reaction from the lower surface of m2 as well. Now look, what m2 is doing, m2 is pressing m1. So m1 will press m2 up. This is a normal reaction on m2 by m1. That's why m2 is not coming downward. Gravity is pulling m2 downward and m1 is pushing it upward. So this normal reaction that we have drawn on m2 is caused by m1. Now at the same time, m2 will be pressing m1. So m2 will be also causing some normal reaction, some normal force on m1. m2 is pressing m1 and m1 is pressing back m2. If you press your hand on a surface, then you are pressing the surface. So this surface will tend to have some deformation because there is some force applied by your hand on the surface. Now at the same time, the surface is also applying some force on you. So the muscle will tend to flatten, because our muscle will be flattened if some force is applied on our palm, and that force is applied by the surface. So this normal reaction always exists in a pair. M2 is pushing M1 downward, it is pressing M1 downward. So M2 is applying some force on M1 downward. That is a normal reaction by M2. In turn, M1 is also pushing M2 up. So M2 will be applying certain force upward on M1 will be applying certain force on M2 upward, and M2 will be applying some force on M1 downward. So when we are concerned with the FBD of M2, we drew only the force acting upon M2. That is a normal reaction by M1 and gravity force. Now we are looking at the normal reaction FBD of M1. So we are looking at all the forces acting on M1. So one of the force we drew as gravity, M1G. The other force is the normal reaction by this surface, N2, and the third normal reaction will be from this surface. Whenever there is a contact and there is two surfaces pressing each other, there will always exist normal reaction between them. So this normal reaction will be same in magnitude as this normal reaction because they are equal and opposite pair. Okay, so M2 is pressing it downward, so the normal reaction by M2 on M1 will be downward. So we can draw it like this. So there are three forces which are acting on M1. Gravity, and there are two contacts we can see, and there are two normal reactions for each. One for each. They are altogether two normal reactions. So while drawing the FBD, what we have to see is all the forces acting on the block, and there are three forces acting on M1. So we have drawn three forces altogether. Okay.